Hi, everyone. My name is Chris Trevetti, and I am a postdoc at the German Research Center for Geosciences, and I am working in the interface geochemistry group, mainly on microbial ecology of glacial systems and how microbes can impact the climate. Today, we're kind of doing a follow-up on Dr. Liz Suter's previous Amplicon analysis using QIIME on Mike Lee's data set using his tutorial. But today I'm going to show you how to do it in R, base R, as opposed to through QIIME, even though QIIME uses DADA2 as well, just so we can get the best of both worlds and kind of compare the results afterwards. And there's a few unique things here. I'm going to be showing you how to do it on my local version of RStudio. However, at some point we want to try and implement this in Cyverse like Dr. Suter did previously. So jumping right in, let me share my screen here. Okay. So I am in the RStudio environment, and what I have here is I've got our lesson in an R Markdown notebook, and I've got the database we'll be using to classify our taxonomy. But just to start up right away, the first thing we want to do is we've provided you with this R script, and as I mentioned, it's based on Mike Lee's, Dr. Mike Lee's Happy Belly Bioinformatics tutorial, which we can see here. And we're basically just following the outline for this, using his data set as well. So it's kind of a walkthrough of this workflow as well. And he actually provides a binder for this, which is another way you can do it. So starting right away, what we need to do first, once we're in R, is we need to install the required tools. Now, many people still use the native naive Bayesian classifier, but for our purposes, we're going to try the new IDTaxa algorithm that's part of the DECIPHER package to do our taxonomy assignment. But that won't come for a bit later. So yeah, so running through, and I already have these packages installed, but I'll go ahead and do it again. So if you use R, you know you can highlight things and then hit Control-Enter on a PC, Windows PC, which I'm using here, or you can hit Command-Enter on your Mac OS. It's asking me to update, so I'll, sure, why not? This is sometimes a bad idea. And if it starts to take too long, I'll skip through this part. But it's always good to make sure that your R instance is updated with whatever packages you're going to be using. It looks like it didn't take too long. And I'm going to go ahead and install DECIPHER as well. Now keep in mind, if you're running an older version of RStudio, the new BIOC manager BIOC manager is what bioconductor used to be, basically where all the bioinformatics, or many of the bioinformatics tools, were housed. So sometimes that doesn't work if you're running an older version of RStudio, because it doesn't like the new BIOC manager. So you may have to install an older version of BIOC manager to work with whatever RStudio version you're using. In this case, I think we're fine. It gave us some warning messages, but you can always check by doing a question mark and whatever tool you're using. So I can do question mark DADA, looks like that's installed. And for DECIPHER, if I could spell, well, it's not working, but one way you can always check that is you can go into your packages here and you can scroll down and it looks like DECIPHER is installed. One reason it may have been unhappy with me and didn't find it is because you actually have to load those libraries once you've installed the packages. Okay. So the other thing that can be an issue, well, I don't want to say it's an issue, but one thing that we're going to do is we want to use CutAdapter to remove our primers. Now, you can do this using DADA2, but for the purposes of following Mike's workflow, we're going to also use CutAdapter to remove primers. The only issue is because I'm using Windows, we can't use the built-in terminal console as part of RStudio because it's not a Linux environment. And the workaround for this is I do have Linux installed, not Linux installed, but WSL, which is kind of Windows subsystem for Linux. And we're going to install it that way. And I can put up some instructions on how to install this as well. So I've already navigated to the folder that our lesson is going to be working in here, and we're going to kind of be going in and out for just a minute here of RStudio and our WSL instance on Windows here, but it'll still work the same. Now, if you are doing this on Windows, you'll need to make sure that you have Conda, Anaconda, or Mini Conda installed, and we'll provide a link to that as well. But so we're going to install CutAdapt in a Conda environment. And one way to tell if you already have Conda installed is you can say which Conda, and it will tell you if you have it installed or where it's installed. So luckily I've already installed that, and I can use this handy command, which basically means using Conda, please install CutAdapt into our base Conda. And this is just saying -C is the Bioconda channel, which is where it's looking for this program. So we will run that. And sometimes it takes a bit. So, okay, it looks like it found it and has some dependencies that it needs. So we can say yes. All right, so if we say which CutAdapt, it shows us that now in our base Miniconda installation or our Miniconda environment, we have CutAdapt. Now you can also use Conda to create virtual environments. So if we only wanted a virtual environment that had Conda installed in it, we could do that as well. In this case, we've just installed it in our base Conda environment. Additionally, we also need to download the data from Mike's Figshare. And I have a link here to his tutorial as well as up here in the title. This CD tilde just means to go home. But if you're already in the folder that you're going to be working in, you don't have to do that. So we're going to download it with this command here. And just so you know, if you do Control-C to copy text, when you want to paste it, you can't do Control-V, you just right-click on your mouse. So slowly downloading that. All right, now if we do ls, we can see that in our folder, we have the RMD file, we have the taxonomy classifier database, and we have the data we just downloaded. Now we can uncompress that with the next command. All right. And then these last two commands are basically going to remove the compressed file and move us into the folder. That was part of it. So now if we do ls, we see we have all the files. We also have all the R files and the R data file that Mike provides as well, but we won't be using those today. And additionally, we have the primers file that we'll need for CutAdapt. If we do cd ... we go up to our previous folder. So let's go back into that one. And remember, anytime you see bash here, that means we're going to be working in that Linux environment. So either in your WSL on Windows or in your terminal in RStudio. Now we're just going to get our sample names. Okay, and now let's remove our primers using CutAdapt. Now the way Mike teaches it, we do it on one sample first to check that it worked, and then we do it on the rest. So we can copy this and just quickly to, and we can look at our CutAdapt version as well, just to see. Apparently I'm using 1.18. I don't know why it didn't download the latest version, even though Mike was using 2.3. Hopefully that won't cause any problems for us. And just to explain a little bit about the code for CutAdapt, here we're actually calling the program. This is our forward primer and its reverse complement. This is our reverse and its reverse complement. Then we're talking about minimum overlaps here to discard untrimmed, and then our output files, and then our two input files at the very bottom here. So hopefully everything goes well here. We can throw that whole thing in. It zooms on by. And now we can check kind of before and after. So before, we see we have this GTGCC, which if we scroll up, GTGCC is right there. And if we look at the after file, we can see that's gone. And ideally, this should match what we see up there, and it looks like it does. And note we still have all our quality information of the FASTQ files. All right, now hopefully we can use this awesome loop that Mike wrote to then run CutAdapt on the rest of the files iteratively. Okay, and so the way he set it up, it will echo which sample it's working on, so we know that it's running through the loop. And don't mind that beep in the background. I think that's my dishwasher just finishing. And while those are running, we can copy this nice little grep command that Mike wrote to look at the output stats. Okay, and what we see here is our output stats. Perfect. And going back to Mike's page, kind of following along where he was at. We're looking at the fraction of reads retained, and it looks to be almost exact. So that's great news. Okay. Now, this is awesome. CutAdapter worked. Everything's going swimmingly. So we can now hop fully back into R and start on the proper DADA2 workflow. Now, I did intend to start this as, or start R as an R project, because that's really nice, because if you have an R project file, what happens if you start R with an R project file, then it immediately starts you in the working directory where your project file is. So there's no confusion about where you're at ever. In this case, though, we're going to go ahead and just set our project file to where we're at. And I hope this works. Actually, what we're going to do instead, if you don't know the actual path, you can always use the set working directory command like this. But if you're already in the folder where you want to set it as your working directory, you can just go to this little more drop down here, and you can say set as working directory. And as you can see, well, actually, no, we can do it in here. Is that going to cause this? Yeah, it might cause this issue. So we're going to go up one level to where all our reads are, and then one more time. So this is the working directory. So you can see it went up one level. Now let's list our files, and we can see all that. And this is basically just listing all the files in our working directory currently. So this includes everything else. And now we're going to set some variables that we can use. And these will go into the R working environment. So we'll set our samples. You can see now that we have a new variable here, a value, and this is our samples. And if you wanted to look at that, you could pop it in there, and you get that list. And then we will also do forward and reverse read variables. Those will populate in there. And then we're going to do variables for the filtered reads. Perfect. And this is all running based on the original sample value that we set. So that's great. And the first thing we're going to do in DADA2, just like we saw in the Chime version, is we're going to look at our quality profiles for our forward and reverse reads. So if we look at all of the forward reads, and sometimes this takes a minute because it's generating all the plots for every sample. And we'll just see what this looks like. As you can see below, if you don't want to plot all of them all at once, because say you have 200 samples, you can just plot a subset of them. But it ended up plotting them all. We can hit zoom to make that little plot bigger, and it will take a second to generate. But they all look generally the same. And note that this data set is Illumina, paired end, 300 base pair reads. So we have our scale down here, all the way to 300, and our quality, Fred quality score here. And forward reads always look great. We won't look at the reverse reads, but we will do this last couple like in the tutorial. And as you may know, reverse reads always look a lot worse than forward reads. So whereas our Fred score maintained pretty far above 30 for almost the whole size of the amplicon, here they definitely start to drop off before 300 base pairs, which will come into play next as we actually trim our reads. So the first big step for DADA2 is to filter and trim your reads. And so we're going to make a new environmental value here called filtered out, and we're going to use the filter and trim command for that. Using our forward reads and then an output for those. And then the specifics we're looking at, the max EE, this is the max number of errors you can encounter before they're kicked out. Removing phi-x, which is basically phage control that they put in, quality control that you can put in when you're doing sequencing. We're going to have a minimum length that we're looking for, 175 in this case. And this is the most important part about filtering and trim, this trunk length, or where to truncate the reads. And on the left, you have your forward reads, and on the right, your reverse reads. And what this means is, at what point do we want to cut out reads if they don't match, in our case, what we're looking for, a certain quality score. So for the reverse reads, we have 200. And if we look at that again, just briefly, that's going to show us that at about 200, we're maintaining Fred quality score above 30. And what that means is one error in every 100 bases. So we want to cut everything beyond that off as we maintain our quality. So let's go ahead and run that. And for the purposes of this tutorial, if anything is going to take a while, like sometimes the error profiles take a while, as well as assigning taxonomy, I will go ahead and run those on my computer, but I'll, just like Mike does, we'll also provide you with an R data file that has all these environmental variables in it, such that if you're just running the tutorial, you don't have to wait for those to run. Or if you don't have the computing power to actually run those in a decent amount of time for yourself, you can just load up that variable and move on to the next step. All right, so that is done now. So we can look at some stats just to see what the filtered out variable looks like. And as Mike shows us, we can use the class command here to figure out what type of data this is in R, and it's a matrix, and then we can use dim to figure out the dimensions. So 20 by 2, so 20 rows by 2 columns. And then if we look at that, we can see for all of our samples, the trimmed files reads in and read out. So how many reads we lost by filtering based on our parameters. Now you can tweak these And I've had to tweak these before. Oftentimes, if you have really, really, really bad reverse reads, you can set this much higher. I've set it to 5, even 7 before, to allow more reads to get through. Yeah. So sometimes you have to tweak your parameters a little bit. Now we can look at the quality of those reverse reads again, just so we can spot check and see, okay, it actually did cut those reads where we thought. And so here's 200, and if we look here, we maintain a very high quality score across at least these 4 reads. But we can ensure that things were trimmed to our liking, and that is good. Now I do make a note here that these numbers are slightly different than Mike's. So if you're running through and you're not seeing exact numbers, that's okay. There's probably variability in the version of DADA2 being used, and other things. So it may not be exact every time. So now we want to do error profiling, and this is something that DADA2 does so that it can infer ASVs later on. It creates an error profile based on your reads, so it knows kind of the proportions of A's to T's, G's to C's, all of that. So then it tries to then infer what would be a true sequence variant or not. This can often take a little while. And also note that here you can use it, you can do it multi-threaded. This depends on the computing power, if you're using a local computer, or if you're using a server, definitely use multi-threading. The reason Mike didn't use it in this case is he was running it through a binder, which often doesn't have great computing power. So you sacrifice speed in that case. But for me, I have an okay computer, so I'm going to try and run it with multi-threading and see what happens. And I'm going to comment out this one because I want them just to run right in a row. And 1 second, I just want to check something. Learn errors. We can look at the help file for learn errors. And I just want to see if you're actually able to tell it how many threads you want it to use. Okay, it says the number of available threads will automatically be determined. I know in some of the other multi-threading ones, you can actually set the number of threads you want DADA2 to use, which can be helpful if you're using a shared server that maybe has 32 cores or threads, and you want to do it as fast as possible. Nobody else is using it. You could set it to use 16 or something if somebody else is using it. So that's always a valuable thing to do. So we're going to start this going. And I will get back to you when this is done, and I'll make note of how long it takes on my system. Okay, we are back now. Oops, let me close this. And let me close this. We're back. Almost 25 minutes later. So it actually took my computer about 12 minutes per set of reads, even with multi-thread, to generate the error profiles. So Mike's computer is definitely faster than mine, but this just shows the benefit of being able to run RStudio or R on a higher performance computer, especially when you need multiple threads for processes of this nature. Anyways, moving on, let's look at our error profiles here. So this is for the forward reads. And generally what you're looking for here is, obviously our red line is our one-to-one distribution. And then the black line, I believe, is the presumed trend, and then the dots are how the samples errors kind of play out. So you just want to make sure that those things match up generally. And in this case, they look like they do. And almost all error profiles I've seen look like this. So DADA2 seems to do a really good job of this. And let's take a look at our reverse reads really quick. And the same. Excuse me. Okay, so it looks like we can move on. That's great. And so the next step in Mike's tutorial, actually, if I can find it, is dereplication. And the DADA2 developers have actually removed this step from their pipeline. And that's because, let's see, where am I? Here's, yeah, so they jump right to sample inference. And that's because they basically baked dereplication into the next step before you want to do it, because it would cause sample inference to take far too long. But I think post version 1.12 of DADA2, it does it on the fly now for sample inference. So this is one of the only things we're skipping over in Mike's workflow. And we can go straight to sample inference. So again, if you're running it in Binder or something, you want to run it without multi-thread. Oh, and another thing, I did look into this. You can specify the number of threads you'd like to use just by putting it in place of true. So if you know you are on a shared server and you can only use 8 threads or 4 threads, you can put that there. So now it's going to do sample inference based on our filtered reads, the error profiles it just generated. And in this case, we're using the pooling method called pseudo. And Mike gives a really good description of it on his website, what the different, or at least why he uses pseudopooling. And basically the idea is that if there are any quote unquote rare taxa that you want to be looking at, by doing pseudopooling, you won't automatically throw out those singletons or rare organisms by just pooling your samples. But by default, DADA2 does pool everything together and infer ASVs that way. So in Mike's workflow, though, he is using pseudopooling, so that's what we'll use here. So let's run that. Oh, and I already broke something. Filter forward reads not found. What did I do? Wrong. I'm sure you already spotted it. Oh, filtered. Oh, okay. I don't know how I had that wrong. Anyways, let's try that again. Okay, and this looks like it's going fairly quick. but I will skip ahead to when these are done. All right, we are back again. It's about 10 minutes later. Took about 5 minutes per set of reads there. And now on to one of the most important parts is the merging of your reads. Probably one of the faster parts, if I remember. But now hopefully we can take all that processing we've done with forward and reverse, and we can merge them together into our final amplicons that we will do our taxonomic assignments on. So we take everything we've generated so far, our ASV inference, our filtered reads, yeah, and then Mike specifies a minimum overlap. This is another kind of quality step. And then also trim overhang equals true, which just allows overhangs, if they somehow go past the end of the other amplicon, or the other side, the other read. I mean, every time I think something goes fast, it does not go fast. I think this is why I don't usually run things on my own computer. Okay, that didn't take too long at all. But one thing I did add that Mike didn't have in his little call here is you can actually, for some of these DADA2 calls or DADA2 scripts, you can add a flag called verbose equals true. So you can kind of get a readout of what's actually happening as it's happening. And this can give you a decent idea of how quickly or slowly things are happening, which is really nice. So now we have this mergers file. And Mike has a few things that you can look at because it's a pretty important file. But these are just things that R allows you to do to see the type of file that's been generated, how large it is. So 20 elements are for the 20 samples. It contains your names for your samples, everything like that. And from there, we're going to create a sequence table, something we're going to call seqtab. So we'll do that, and then again, we'll look at the class type and the dimensions. It's another matrix, and now we can see of the 20 samples that we have, within that we have 2,521 ASVs that were inferred from the data. That's great. But our next step is we want to remove chimeras. Basically our last quality check step. And actually verbose is part of this script here. So let's do that. And we'll see how long it takes. Okay, not too bad. Only 2 minutes or so there. And we can see we're getting the same numbers that Mike got. So 17 bimeras out of 2521 input sequences. But as it mentions here, those 17 sequences could be associated with a number of reads. So one way to check that is we can look at our no chimera seqtab table and our original seqtab table. And just like Mike, we see that 99% of the reads are still there. So we didn't lose a lot of data. And now is a good time to get a summary of the reads through the pipeline. And we do that with this little function here. And we can run all this together. And this is basically just creating a data frame from all the little variables that we've generated throughout this whole pipeline, and then looking how the read numbers decrease over time. And so we can see, for example, for B1, our input was 1,600 reads. By the time we get our non-chimera check reads, we have 1,400 left, so we retained 90%. And so these values are generally pretty good. I think the developer of DADA2 at one point said, you can expect around 20 to 30% of your reads to be lost throughout the pipeline, which is okay. And with the depth of sequencing that is occurring these days, you can still have hundreds of thousands of reads left over. So that's not too bad at all. So now this is where we're going to diverge from Mike's workflow a little bit. In his workflow, he assigns taxonomy using the RDP naive Bayesian classifier, which is built in to DADA2. But they've recently allowed for using IDTaxa, which is part of the DECIPHER package, and supposedly faster. So I thought we would try this and see how the results look. So I've kind of baked that into my workflow. And right here I have, the latest training set is based on Silva 138, but I believe Dr. Suter ran hers with Silva 132, so I've actually included that in our files, and that's what we're going to be running it with. Now let me make sure I know where I'm at. So 132, we need to load that. And let me make sure I have the correct file path. And if you don't remember what your working directory is, you can do that. And so this is our working directory based on what we set earlier. So I actually need to make sure everything looks proper and it doesn't have 2019 in the title. And I think I can designate the 2 dots for it to go up. All right. Let's make sure I do this correctly. So I'm going to run through one by one. And this is just how it's kind of modifying the data to be able to put into IDTaxa. Let's see if I can load that appropriately. And it should load, so the IDTaxas databases are actually in .r data files. So it should load this into our global environment here. Okay, and it loaded our training set. That is great. And now we're going to use IDTaxa to call everything. I'm actually not sure how long this takes, so we'll find out. Okay, that is finally done. It actually took my computer about 45 minutes to do the taxonomy assignments, which is much longer than it took Mike's computer and or doing it in the binder. So your mileage will definitely vary based on the type of system you're running your data set on. That being said, we are now done with that, and we can do the last set of things or transformations of the data to put it in a format just like how DADA2 would do it. And we will run those quickly. All right, now we have this tax ID, which is pretty much synonymous with what taxa would be in DADA2. And the last thing we can do is just take a quick look to make sure some of the assignments look like what we would hope they would look like. And I did that wrong. Let me, oh, that's because I had taxa ID. Let's do this. Okay, and we have taxonomic assignments. So that's great. And in some later tutorials, we'll actually compare that data. And the last thing you can do is you can export this data, and I've added this in here, but I'm not going to do it now. But this is also from Mike's tutorial. But basically extracting your the standard goods, as he calls them, from DADA2, which would include a taxa table, accounts table, and things of that nature that we can use downstream in other programs or outside of R if we want. But that's it for now. I think the total time for all of processing for me took around 1 hour and 15 minutes. But yeah, so that's what it's like to run it DADA2 natively through RStudio. And in follow-up episodes, I'm sure we'll compare that and we'll see what the differences are. So thanks for joining me, and we'll see you later.